Hi guys. Actually, I'll change that. Hi guys, girls, and non-binary pals. Hope you're all well. This is your awkward Indian linguist back with another video again on parsing. So it's sort of a follow-up on the previous tutorial that I did a few days ago. So today we'll talk about parsing. We'll look at some specific examples. So I have some hands-on examples for you. I'm super excited about this tutorial because I have a lot to say and there are many new things which will come up for discussion, and I hope you will all enjoy it as much as I did preparing for this. So today, like I said, we'll look at different methods of parsing. Okay, so we will see what a parser does, how to write a grammar. So the most important thing is this is for linguists transitioning into text. So I'll show you how to write grammars which you already know, and we'll see how to use those grammars to parse sentences. Okay, and you are familiar with parse trees, so we'll just see how to build automatic parsers. Okay, but before I do that, so I want to kind of there is a preamble here, and I was actually debating with myself whether I should do it before showing you the code or after showing you the code. And I thought that it's good to do it before showing you the code, because this will set the context for the entire discussion. So today, like I mentioned in the previous video, there are many connections between grammar formalisms and parsing, right? But it's so strange that both these communities don't talk as much as they should to each other, and this can be I mean so I don't really have a coherent way of talking about this. I mean, I actually do have a coherent way, but I don't want to open the whole Pandora's box and get into that issue. But I'll just say that for whatever reason we have the situation where the linguists and computational linguists sort of diverged at some point. And so NLP, computational linguistics, and theoretical linguistics, mainstream linguistics, they don't talk to each other as much as they should, although they work on similar things. They have similar goals, but then they sort of each does not acknowledge the contributions of the other. I mean, I can't say that does not acknowledge, but you don't see that happening. You don't see the amount of synergy that should be there. And as I mentioned many times, this is detrimental to both. This has been detrimental to both NLP and linguistics, right? So so I want to kind of start with that. So the thing that we'll see in this video is that these connections between these two areas are so strong, right? There is actually no reason that people could not have developed great grammatical theories with parsers as proof of concepts, whether that theory actually works, and does it have enough coverage to parse parse the majority of constructions in a given language, and can it be extended to other languages. So that sort of synergy has not happened, and I don't know what the reasons are. I mean, as I mentioned, I mean the people who are senior in the field, they probably know the reasons. So it's like, okay, Chomsky didn't acknowledge us, or we don't acknowledge this sort of work. So it's this has been really unhealthy for the whole community, right? Because the big guys are fighting among each other, and who is suffering? The people who are suffering are the youngsters who come into the field with a lot of excitement, a lot of positive energy, and they are open-minded, they want to learn. And instead of getting exposure to this rich areas, different sub areas of linguistics, what they get to hear are these stories. Okay, they don't get along, they don't like us, it's our theory, their theory, we are the good guys, they are the bad guys. This sort of culture has been there. And so this is, I think, very damaging. and I think it's time for us to change it, right? And the onus is on us, the younger generation of linguists who have significant background in linguistics and who are actually now in tech and who are actually working in tech, who know the the intricacies of transitioning to tech, etc. So the onus is on us, and also it's an open source project, so all of us are equally responsible. So it's not any one person's personal project, but it's an open source thing, and we should all contribute to this and make sure that within the next few years there is there is a significant improvement. So there is an interdisciplinary environment in which people from different majors are collaborating with each other. They are not talking down to each other. They are not putting each other down. Oh, you linguists, you don't know how to do this, or oh, you computer scientists, you don't know how to do this, or that sort of thing needs to go. And within the next 5 years we have to develop a sort of culture where, what is the problem with this sort of existing culture? So the external community has no clue what linguistics is, because all the energy of the past generation of linguists went into this sort of infighting. They didn't really present the field in a way that is appealing to the larger community. So people don't know what linguists work on. They have no idea. They think so I'm not going to get into that rank, but let me just say that linguists have worked on very interesting problems. They've developed many rich ideas, and all those ideas are hidden in the books right now. So they're all in the books and nobody really knows about them. So we need to transfer that knowledge and bring it into the forefront of tech. So we have to apply that knowledge, show that all that knowledge is applicable in tech, and also change tech, because tech is also very monodimensional at the moment. So you need to kind of improve the richness. So you don't want like a superficial for everything. Okay, I'll train a neural model, I'll train a neural network. So that's not the only approach, right? So there is a lot of work on grammatical formalisms. There is a lot of work. So there are people have people have worked for decades on these kind of topics, where what's the structure of the grammar, what's the nature of the grammar that humans have. Is it a context-free grammar, and what aspects of human language can be captured using context-free grammar? And if it's a context-free grammar, can you build efficient parsers, and can the parser predict which sentences are likely to be ambiguous? So if there is all those garden path sentences, right? So can you make a prediction that, okay, these sentences are going to be tough to process because the humans are operating with this grammar. So there is a lot of rich ideas, not just in syntax, even in phonetics, phonology. Linguists, phoneticians have studied so much about they know a lot about spectrograms. They know a lot about the speech signal. They know a lot about the acoustic correlates. So how do you spot these kind of sounds in the spectrogram? How do you spot? So there is a lot of rich work which is all hidden in the books, because nobody will talk about it, and nobody will bridge this gap between the tech community and the linguistics community. So it's time to change this. So this is my rant, but I think this will set the tone for the rest of the tutorial, and I'm really excited today. I hope you like it as much as I did. And as I mentioned, we will look at parsing, and the only thing so the most important thing I want you to remember at all times is you don't need any special background. So everything you can pick up, everything is super easy. And today, I started 15 years ago in my senior year project. So at that time there were no packages, no nothing. So now everything is available in neat packages. You can explore everything and learn everything. So the sky is the limit. So don't sell yourself a small dream. So it doesn't matter where you're from, doesn't matter which passport you hold, doesn't matter whether you are born into some upper class family or whatever. It doesn't matter. None of that matters. you could be living in an igloo in Greenland, or if you could be living, in Mongolia and Siberia. You could be living in, like, in the hills you could be an indigenous tribal Dravidian speaking tribal in the hills in Andhra Pradesh. So it doesn't matter, as long as you just have to understand these concepts and then do it. Just do it by yourself. Yeah, there is no barrier here. So it's completely, whatever I know, I'm going to share with you guys, and I want you all to enjoy linguistics as much as I do. So yeah, with that, I think I'll move to the tutorial, and see you soon. Hey guys, so I'm just starting up my PyCharm, okay, and okay, just close this. Okay, hope you can see my yeah, so this is the notebook I have. So yeah, we'll go through each of these steps and we'll talk about everything here. So I think I'll clear all outputs and we'll start from scratch. Yeah. So okay, so today the tutorial will cover, as I mentioned, it will cover context-free grammars, and we'll talk about how to write context-free grammars, which you are already familiar with, and how to use them for parsing. Okay, and all of these are neatly packaged in the NLTK Natural Language Toolkit, the Python package. So you just have to install it, and here is the, how you install it. So I already have it installed, so I commented it, and then you import the CFG, right? So this is the class that we'll be using. So yeah, the CFG class has a method where you can actually read the CFG, the context-free grammar, from the string. So here I have a string. So recall that this is the same example that I showed you. Very simple context-free grammar where you have S NP VP, NP goes to determiner noun, determiner is the, and noun is, it can either be cat or rat, and then a verb goes to V and P, and the verb is ate. So it can parse two sentences. One is the cat ate the rat, and the other is the rat ate the cat. So these are the two sentences that it can parse, or it can generate. So whether it's generation or parsing is both the same. So okay, so let's read the grammar. Okay, so you have the grammar, and there are 7 rules. So the grammar that we wrote here has 7 rules. So let's take a look at the rules that were. Yeah, so S goes to NP-VP, NP goes to det N, determiner is the, noun goes to cat, noun goes to rat. So yeah, so basically it broke this rule into 2 rules, right? And then VP goes to VNP, and V goes to 8. So yeah, in CFGs there is this notion of Chomsky normal form. This is also known as the Backus-Naur form. So Chomsky normal form means that RHS has only a maximum of 2 non-terminals. So here you see that there are 2 non-terminals. Here again you have 2 non-terminals. Actually, yeah. So yeah, maybe I think I should run this step first. So yeah. So anyway, so the point is that you should have max 2 non-terminals in the right-hand side. So in other words, it should be a binary branching tree. You can't have from one node. You can't have like 3 different non-terminals. So as you can see, the grammar is already sort of, you don't have any ternary branching here. So yes, the grammar is Chomsky normal form, is in Chomsky normal form. So we also discussed the concept of terminals and non-terminals, right? So terminal is a node which cannot be expanded anymore. So that would be things like cat, rat, ate, the. And non-terminal is something which can be expanded further. So I wrote a small function here to extract the non-terminals and terminals. And so this is just based on our definition. So non-terminal is anything which can occur in the left-hand side of the rule, right? And terminals, some of the non-terminals also occur in the right hand side, but then terminals all only occur in the right hand side. So you have a list comprehension statement here. So it has to be in the RHS, and it has to not be a non-terminal. It should not be in the set of non-terminals that we already extracted. Okay, so this is a basic function. Okay, and now let's see what it does. Yep. So you got the non-terminals and the terminals. So det, noun, NP, S, V, VP, these are the non-terminals, and these words are the terminals. So yes, as simple as that. So now you have a grammar, you know what are the terminals, non-terminals. This is what you need to know, and you already know how to write this grammar, right? So these are things which you would have learned in your syntax courses. So now we can use this grammar to parse a sentence. Okay, so we'll see how to do that. And there are many different, so as I mentioned, there has been work on building different sorts of context-free grammar parsers, and there are so many different kinds of parsers. I don't think I can cover all those things in one tutorial. So if you look at the NLTK documentation, so this is actually the NLTK the book that comes with the package, and so this is all freely available. So there is so this chapter 8. So chapter 8 is about analyzing sentence structure. So this has a ton of information. So you actually don't even need to watch my full tutorial. So you have so much more, but my job here is to sort of make some of that accessible to you easily, so that you feel interested enough to go and read this whole chapter. But as you can see here, there are so many different kinds of parsing techniques which have been developed: recursive descent parsing, shift reduce parsing, then you have left corner parsing, so all sorts of things. So top down, bottom up. So these are some terms that you will see. So here I'll just use a simple shift reduce parser. So you should read about what a shift reduce parser does. But the point here to notice is that you can just you can create an instance of the parser with the grammar that you wrote, this small toy grammar. Okay, so let's see what it does. So now you have these two sentences, right? So as I mentioned, these are the only sentences that this grammar can analyze. So if you have a sentence with a word which is not in these words, so ate, cat, rat, if you have a sentence which has a word which is not in this list, then the sentence falls outside the coverage of your parser. So it can't parse such sentences. So here, the two sentences that this parser can parse are these, right? And now let's look at the output. Actually, so it's just sentence 1 that we'll look at the output. So so this is the parse. So this is what is called a bracketed notation. So in the parsing literature, they use this notation, but it's basically the equivalent of your tree. So I'll show you that just to show that this is equivalent to the tree that you see in your syntax textbooks. So NLTK has a package which is called tree, and I just copy pasted this and loaded it into a tree from string, and then I do pretty print. See? Boom, you have the tree that you're familiar with. So S goes to NP, VP, NP goes to det N, VP goes to V, NP, and NP goes to det N. And you have the sentence parsed, right? The same way, the second sentence can also be parsed. Now it's the rat ate the cat, right? So this sentence is also parsed by the grammar because all the words in the sentence have, are covered by our grammar. So now let's extend this grammar. So suppose you are asked to, extend the coverage of the grammar to cover this sentence. The boy ate the soup. So how can you do that? The verb is the same. You just have to add boy and soup to your rule for the noun, right? So you just have to change one rule, as I mentioned here in the comment. So instead of cat, rat, earlier there was just cat and rat in the noun, so you need to add boy and soup. So this is again quite simple and straightforward. So you have, an object called, you have a class called production, and then you have a class called non-terminal. Yeah, so these things, I think you should spend some time. And it's fun, right? Like once you start playing around with these things and you're able to build your own mini parsers, it gets more exciting, right? So all the knowledge that you have of linguistics, you can actually implement it and see how, all of it makes total sense. So yeah, so what we do here in this statement is we are adding some production rules to the existing grammar. So we already have a grammar. So I'm adding these two rules. So I'm adding one rule which is non-terminal noun goes to boy. The other is non-terminal noun goes to soup. So I extend. So extend function adds these elements to the list, which is the grammar. The production rules is already a list. So it just adds these new rules, right? So then I again, create a CFG with this new set of rules. So yeah, so here you mentioned that the start symbol in this grammar is S, and you create a new grammar object. So let's do this. Yeah, so it's done. So now let's look at the production rules again. And there you have. So the new rules are added to the grammar now. Noun goes to soup, noun goes to boy. So now let's try to parse this new sentence that we have. So now you can parse the new sentence. The boy ate the soup. So again, yeah, you can visualize this bracketed notation, the parse tree in the bracketed notation this way. But I think I'll leave that to you. You can do it. So yeah, so this was a toy CFG, right? So things were very simple. But then you can imagine that, you have to parse thousands and thousands of sentences. So natural language, the most important aspect of natural language is it's an open-ended set, right? So no matter how big your corpus is, you can create a new sentence which will not be in the corpus. So your parser has to parse all the sentences, right? So how does it do that? So, in a realistic scenario, you'll have a large grammar. It won't be a small grammar. It will be a huge grammar with many thousands of rules, as I mentioned here. So there is one such grammar which is available in the NLTK package, which is the Attis grammar. So I thought that it will be a good idea to kind of see that, how that grammar looks. So yeah, so you kind of loaded the grammar, right? So this grammar is the Attis grammar. So it has, as you can see, 5,517 production rules. So now let's look at the top. Yeah, so let's look at 20 of these rules. See, you can see that there are very, very complex rules. So like, yeah, adjective, only, adjective, such, adjective, and so basically other, last, so, and then cardinal, adjective, cardinal, 7, cardinal, 300, right? So you'll have many, and then what do you see here? So when you have an NP, this is a special kind of NP, you have all of these different sorts of, quantifier phrase, cardinal, then adjective phrase, noun, then after that, some sort of participle. So yeah, so these are all, this is a tag set used by the grammar, so you can look up the tag set. But what do you see here? You see that one non-terminal can go to more than two non-terminals. So the RHS contains more than two non-terminals. So recall our definition of Chomsky normal form. So would this grammar be in the Chomsky normal form? Let's check. No, so this is not in the Chomsky normal form, so false. So this is sort of, you understand this, right? So it's because you have more than two non-terminals. And yeah, let's try to load the sentence. So again, there is a set of sentences that this grammar can parse. As I mentioned, no matter how big your grammar, it will still have limitations. There will still be a sentence for which you might not have a rule. And yeah, so in language, the magnitude, the dimensions of language are huge, right? Like you have typically, you have around the order of nouns is approximately like if you have 5,000 nouns, you have like 500 verbs, and then you have around 50 function words, and then you can combine them to create any number of sentences. So unless you have coverage for all the high frequency items, the grammar will not have broad coverage, and even in a broad coverage grammar, there'll be a sentence for which it breaks. So yeah, so they have a set of sentences that this grammar has coverage for. So we extract the test set. So there are 98 sentences in this test set. So we'll just look at one. I took sentence 15 just as a random example. So yeah, so the sentence is, can you tell me about the flights from St. Petersburg to Toronto again? So this is the sentence. So now again, let's parse this sentence using the grammar that we have, the large grammar, the Attis grammar. Okay, so this time I'm using a different sort of parser, so a bottom-up chart parser. So again, please go back and read about these parsers. So I mean, if I get into the details of each and every parser, then I think it would be, and there is actually a lot of information here, so I don't have to repeat all that. So you can slowly understand bit by bit, but I'm just giving you a high-level overview here. So yeah, so we now created a new instance of a bottom-up chart parser and loaded this grammar into it. So now we'll try to parse this sentence here. Can you tell me? Okay. And yeah, so let's see what we have. So we actually have 3 different parse trees for this sentence. So this is the first one, and this is the second parse, and this is the third parse. So this is one of the issues, right, with building automatic parsers. So your grammar will have some inherent ambiguity. So there will be more than one way of parsing a sentence given a grammar. So as you can see, even with a realistic grammar, you have 3 different, so as the number of rules increases, there'll be, multiple possibilities to expand a particular non-terminal. And based on that, you will get like different parse trees. Okay, so let's actually compare this thing. So for example, here, right? So here the main difference is, I'll leave it to you, but I'll point out the main difference here. So here, if you see the noun phrase, so St. Petersburg is treated as one noun. Okay, but then there is another rule in the grammar which says that, Saint is like is a sort of a, that itself is a noun phrase, and then Petersburg is like modifying. So there is a relationship between, so here it's treating it as a multi-word expression, so here it's treating it as 2 different nodes. So both are equally, plausible, but the question is, so I mean, what sort of representation? So this will vary from context to context, which tree is the right one. Okay, so but this is a problem with CFGs. So this is why, we'll talk about, probabilistic CFGs, why we need to bring in probability to see, like, which of these 3 trees, how can you pick the best among the 3 trees. So we have to incorporate the notion of probability here. But yeah, so like here, all you need to notice is that with the grammar, it was able to parse this sentence. Okay, so yeah, so 3 possible ways to parse the sentence. Which one is correct? We don't know. And this is where we need probabilistic CFGs, and this will be the next session. So, and then finally, this is the part that, I want you to follow carefully. So there is only one requirement that the CFG parsing for the CFG parsing algorithms, and that is that the grammar needs to be a CFG. It can be any style. So you can also parse using an X-bar style grammar. Okay, so it's not true that Chomskyan grammars are not computational. So it's not, or I should actually change this. I'll say, I don't want to use the phrase Chomskyan grammar, but yeah, it's not true that theoretical grammars are not computational. So as long as your grammar is a CFG, as long as you write your grammar as a CFG, you can use that to parse a sentence. And it's just, as I mentioned in the preamble, it's just cultural reasons. People don't like so the parsing guys will not acknowledge They will never talk about X bar theory. The X bar guys will never talk about the parsing. So yeah, so that's what I was referring to in the preamble. So here, just to sort of show you that this can be done, I wrote a small X bar grammar, again toy grammar. Okay, and yeah, so I just wrote this quickly. Okay, so now we have the grammar loaded into a CFG object again, right? So now let's look at the production rules. So these are the production rules. So you have NP goes to spec N bar goes to N bar PP. So this is when you have adjunction, right? And then you have N bar goes to N PP. So this is when PP is the argument, right? So when you have, yeah, so all these rules I'll leave it to you to explore them. But this is the small test sentence that I have. So the book of poems with a dark red cover. This is the example that I want to parse. So again, I took the same parser that we took. You can take any parser as long as it's a CFG, it will work. And yeah, so let's try this. So yeah, now you have the ambiguity problem. So the grammar that we wrote here actually generates 6 different parse trees. And you can actually see the reason, because you see N bar, right? So there are 2 possible expansions here, actually 3 possible expansions. AP N bar, so when you have an adjective phrase, there you have, so when you have the more the number of expansions for a rule, the more ambiguity there will be. So you have 6 possible ways to parse the tree, parse the string, which is this one, the book of poems with the dark red cover. So yeah, so just as an example, yeah, to kind of let's inspect the tree. So I took the first 2 ones, okay, and again visualize them as trees. Yeah, so this is the first one. So spec the, and then N bar. So yeah, this is wrong, right? Why? Because of poems, which is actually an argument of book, is being treated as an adjunct, and it's being treated as an adjunct the same way with the dark red cover is being treated as an adjunct. But if they are adjuncts, both are adjuncts, it should be possible to reorder them, but you can't do that because this one is actually an argument. So a book of poems is an argument of book. So yeah, so this is not right. So then we go on to the next option, and here you see that yeah, we get the desired thing now. So here NPP, PP is this, PP the of poems is the argument of book, and then this one is the adjunct, and then you can see everywhere all the spec and everything. So yeah, all the details are there. So yeah, I did this to show you that there is actually no conflict between the frameworks themselves. So X bar grammars can be used to do parsing. It's just that you have to write the grammar in a way that is creative, so which will take care of this ambiguity. So you don't want like you want to write the grammar. So that's why writing a concise grammar, precise grammar that generates only the grammatical strings in a language is such a task of genius, right? It's a task of like Panini's grammar, right? So I mean, there's work on this. So by Wiebke Peterson, if I remember. So I think yeah, she's a professor in Germany. So she has her whole thesis is about showing how Panini's grammar is so optimal. So out of like many options, it just picks like the right. There are various ways to write the grammar, but it picks the way which is like the most optimal solution. So yeah, anyway, so grammar writing is a great skill, and if you do this every day, then you will become so good at it. So yeah, so in one of my previous jobs, my job, because of NDA I can't give you more details, but my job was basically to write grammars, Chomsky normal form, Bacchus norm form grammars, and they have very interesting applications like in the smart devices like Alexa, Google Home, etc. So I can't tell you more than that, but yeah, so this is a very useful skill to have in the industry. So writing grammars, and then also if you know about the parsing bit, and if you're open-minded to learn about these 2 things and combine the 2, then I think great things can happen, and we'll change the existing culture as well, where these 2 communities are not talking to each other. So yeah, so this I did it mainly for this reason, to show that X bar theory is not super different from like a standard CFG. So yeah, one of the disadvantages of X bar is, as you have like every it's quite detailed, so it has all these bar levels. So for each phrase you will have quite a lot of structure, and as the sentence gets longer and longer, the tree will become bulkier and bulkier. But it's kind of it's a good thing if the bulkiness is justified, if you can show that all these bar levels have some psychological reality or have some importance. But if if in an NLP application, if you don't need these bar levels, I think I would say that it's better to go for like a lightweight CFG like this. So these are the kind of CFGs that like that work the best, for which you have very efficient parsing algorithms. So but then even an X bar grammar, if you are good at it and if you write it creatively, then there is it's a CFG. So until you bring in like things like movement, etc., and then also the differences between the different spec positions. So if you want to treat the spec of NP differently from the spec of VP, and differently from the spec of like AP, right, adjective phrase, then those are context sensitive elements in the grammar. So yeah, as I mentioned in the previous video, Chomsky said that natural language is mildly context sensitive, so it's somewhere between type 1 and type 2 language, so between a context free and a context sensitive language. So when linguists developed these formalisms like X bar, they made sure that there were some extra mechanisms to model the context sensitivity. So that's why you have all of these devices. But yeah, here, to keep things simple, I treat all specs the same and there is no movement. And you can see that you can parse strings exactly the way you can parse with any other CFG. Okay, so I think this was enough content for this video. I hope you like it, and if you did, do subscribe to my channel. You'll see a lot more content like this. And then in the next video we'll talk about probabilistic CFGs. And in the meantime, I recommend reading this chapter from the NLTK book, chapter 8, and also playing around with various parsers. So yeah, this is another page which is very good. So the API reference for that page, so the documentation, so this is really good. So this has a lot of stuff. So most of the things that I did in this tutorial come from there, although I didn't copy paste any code. So I kind of took my own examples and wrote my own CFG. Okay, so hope you guys have fun, and it was really fun to prepare for this tutorial, and see you again next time. Until then, have fun.